In 1922, the Stern Gerlach experiment fired a beam of silver atoms through an inhomogeneous magnetic field and split it in two. While the setup was designed to test space quantization, it inadvertently captured the exact data needed to calculate the electron's intrinsic magnetic moment. To understand the math, we have to look at the hardware. Otto Stern and Walther Gerlach used this vacuum-sealed apparatus of glass and pumps to isolate an atomic beam, creating an environment where every physical variable could be strictly controlled. Silver was the ideal candidate because of its ground state configuration. Of its 47 electrons, 46 are paired off in a way that cancels their magnetic effects. That leaves one unpaired electron in the 5s orbital. Since this orbital has zero angular momentum, it simplifies our calculation.
With zero orbital interference, any magnetic deflection these atoms experience as they travel through the field is driven by the intrinsic spin of that single outer electron. To find the particle's deflection, we first define its vertical acceleration. This left equation gives the magnetic force on a dipole in a field gradient. Setting it equal to Newton's second law on the right isolates the exact acceleration of the silver atom. Next, we determine how long the atom is subjected to this force. We take the physical length of the magnet and divide it by the atom's horizontal velocity to find the total travel time. Now we use the classical formula for distance under constant acceleration. By inserting our values for acceleration and time into this baseline, we can predict the final deflection. After simplifying the algebra, we arrive at the master deflection equation for the Stern Gerlach setup. This expression allows us to calculate microscopic quantum properties directly from macroscopic measurements, like magnet length, field gradient, and particle velocity. Pause the video and try to solve for the atomic magnetic moment, μ(z), using the original 1922 data. Pay close attention to how the beam separation value is defined in the table. To find the deflection for a single beam, we must use the distance from the center to one dot. The 0.2 mm measurement is the total separation between both beams, so delta z is exactly half of that total distance. Plugging these corrected values into our isolated equation results in 9.274 times 10 to the negative 24th joules per Tesla. This value is precisely 1 Bohr magneton. Because the math resolved to a clean integer of exactly 1, the researchers in 1922 had no reason to suspect that this result was actually the product of two separate quantum factors canceling each other out. We can see the discrepancy by looking at the modern quantum operator formula. While orbital momentum has a g factor of 1, the electron is a spin 1/2 particle, which changes the relationship between spin and magnetic moment. When we substitute our calculated 1 Bohr magneton on the left and the known electron spin of 1/2 on the right, the equation reveals a specific requirement for the g-factor. For the math to resolve to the 1 Bohr magneton we measured earlier, the electron g-factor must be 2. This factor of 2 perfectly offsets the spin value of 1/2, creating the numerical result that Stern and Gerlach observed. It wasn't until 1928 that Paul Dirac's relativistic theory provided the first principles proof that the electron's intrinsic g-factor was indeed 2. Later, physicists like Julian Schwinger used quantum electrodynamics to show the value is slightly higher than 2, a discovery that remains one of the most precisely verified predictions in physics. By working through these steps, you've used a century-old experiment to connect macroscopic forces and kinematics to the precise quantum mechanics of the electron.